So thanks everyone for joining, and thanks Giovanni for accepting. So today we have the honor of having Giovanni Ballarini. So Giovanni is doing his postdoc with Ludmila Grigoreva, who's also in the audience, at St. Gallen. So Giovanni, before he did his PhD in economics, and University of Mannheim in the Graduate School of Economics and Social Sciences there. And his research is actually, I think, pretty interesting. So it's in the intersection, in my mind, of, I guess, neural networks, non-parametric statistics, and time series analysis. And there seems to be a decent focus on finance and microeconomics. And so this paper I found quite interesting. So I'm pretty looking forward to today's talk very much. So today he's talking about the memory capacity of recurrent neural networks, the good, the bad, and the ugly, which is slightly different than the original title, but even better, I have to say. Okay, so after you.
Thanks so much, Anastasis. Let me thank you again for the great introduction, of course, and also for inviting me and organizing the seminar. So it's great to be here in different time zone, but it's fantastic to be able to present this work. So as Anastasis said, so I slightly changed the title in the sense that I try to be a little bit more, let's say, clever. So this is a clear reference to Sergio Leone's famous film. All of you probably know it, but I think you'll see, I hope, at least during the talk, that indeed, if you think about the setting that we are going to work in, which I'm going to introduce in a second about memory capacity of recurrent networks, there are some good things. And I will talk about, I think, quite explicitly about what those are. Those aren't that many, and that's why the bad and the ugly will come in. So this is actually coming from two papers that I'm going to introduce pretty soon, joined with Ludmila and Juan Pablo. This is something that we have been working on in different, let's say, from different perspectives for a couple of years now. And so this presentation, I thought, was the perfect opportunity to make a rejoiner and kind of really talk about the topic from these different perspectives that we have collected a little bit. So I'm going to talk actually about both a linear case and a nonlinear case, and this kind of covers kind of the land of the settings of interests. So without much further ado, let me just introduce the general setup that I'm going to be talking about, which is going to be the standard one in some sense, if you know this literature a little bit. So in a broad sense, we're going to talk about state space systems, which are given by these two equations, 1 and 2. So the first one is the state equation, xt, which is a vector in Rn, is some function of the previous state, xt minus 1, and some sequence of inputs, zt. And then we have the observation equation here in this abstract form where you have yt, which is a target that or like a feature that you might be interested in predicting with this function h, which depends on parameter phi's, and these are a simple function of the states, right? So this setup embeds, let's say, a lot of classical state space models. For example, if you come from econometrics like kind of I do, nonlinear, for example, state space models, but also recurrent neural networks of the classical kind. The point that I'm going to be stressing a little bit on is that we're going to focus on a specific setting where f I'm going to assume is a fixed or given map to you. So you can think of this as a pre-trained RNN layer. In fact, we're going to talk about random weights, which I'm going to introduce very, very soon, neural networks, in the next slide, in fact. And this is because there's this huge literature on reservoir computing where you don't really train this equation one. You kind of sample it from some usually cleverly designed distribution or well posed distribution for the task at hand, and you only need to parameterize this a lower h phi function and estimate the phi from data. So the quantity that we're going to be interested in is the so-called memory capacity. So this is a long history because it's a, let's say, very intuitive measure to define. So you think about the sequence of past inputs that we're trying to embed in our, well, I'm not sure embed is the geometrically the perfect term, but let's say collect into our state, right? XT, we want to be able to somehow characterize an ability of this model to recombine the states and extract the dynamic features of the process signals. And this means being able somehow to go back in time, right? If we want to extract something that happened a few periods ago. And so this definition here, this is one reference. This is this Jaeger 2002, which introduced it for the concept of ESNs, which I'm going to talk about very soon. But you can see that the memory capacity in 3 at the certain lag order. So a positive lag means 0 steps in the past, so contemporaneous one step in the past, and so on, is just a measure of how well you can reconstruct at that specific lag the previous so input zt minus tau with h of phi tau now because we do a projection of the state or a function of the state that depends specifically on the tau lag, and we try to predict this in MSE error, so mean square error, right? And then if you normalize by the variance of the inputs and you subtract it to 1, you get a very nice and normalized measure of how this reconstruction goes. So again, this is a specific setup. We're working in the L2 setting, and we are going to soon see a more simplified setup specific to ESNs. The mapping from tau to MC tau, so from the memory capacity at that lag, is the so-called memory curve. And I'm just going to show you a picture here to kind of have an intuitive understanding of what I'm going to be talking about for the remainder of the talk, right? So if you think about tau growing here for a network, so for a recurrent size of 100, you're going to see that the memory capacity is very high at the beginning here around until around 50, and then at some point drops because at least arguably you're not able to embed an infinite history into a finite dimensional state. So there is a limit basically to how much we can remember with recurrent neural networks, which is something that people have also studied very well because it connects to, let's say, the exploding gradient problem, et cetera, and et cetera. So this is kind of an important problem from a number of perspectives. So one last quantity that is very important is if you sum from 0 to all the way to infinity, these memory capacities, which are strictly positive quantities, you're going to get the total memory capacity of your model. This is specifically important quantity because people oftentimes try to maximize this. And in fact, one can prove, and this goes back all the way to the original paper by Jaeger, but also to Maurice's contribution, for example, in continuous time. In our setting, the bound of interest will be the memory capacity goes all the way from 1, which is the worst case. You can only basically, you have no memory. You can only remember the present to some extent. Or you can remember all the way in some sense to n, so to the size of your state. So of course this is the sum of all the memory capacity. It doesn't give you of all the overall the lag, so it doesn't give you granular information of how this information is encoded at each individual lag, but it does tell you something about how much memory there is in the system, and this is why people are interested in this metric. So in practice, what people have observed is that the estimated memory capacity, total memory capacity, fluctuates a lot depending on the state map, and also depending a little bit on the output map, but mostly people have focused a lot on the state equation. And so the question that we started with really was, can we say something more about the memory capacity in both flavors, in theory, in practice, that is a little bit more precise than this bound this interval 1 to n, or if you want normalize 0 to 1.
Can I ask a
So
question?
this was the sorry.
So can I ask a quick question?
Yes.
I'm still like replaying the definition of memory capacity tau in my head, but just to know. So I guess this depends on the target time series y, I guess, right? So I'm just curious that why is n upper bound? Like for example, if you have a constant time series, uh, couldn't yeah, just understand like why n is upper bound.
So we're going to talk mostly about the stochastic case. So usually you just
Okay.
think about like IID inputs, and so
Okay.
you don't have these kind of degenerate setups.
Okay.
Um,
Cool.
and so in that case, you do get this bound for very general series. I mean, you can also implement it for
I see.
stationary. This is what we have in the paper. Yeah.
Fair. Complete sense.
Okay.
Thanks.
Yeah, sorry. Yeah, perhaps I didn't explicitly mention that. Yes, we're going to be interested in stochastic inputs of some
Okay.
kind.
Cool.
Thanks for the question. Okay, so I just wanted to show you like a very high level kind of review, if you want, of this memory problem in recurrent and reservoir models. So this is specific, this literature review is specifically focused on reservoir model because this is what we're going to talk about. And there are many things that you can look into. So that this is uh, some of the references that we have in our that we have to collect. So something about defining memory capacity. Some papers work a lot on memory properties that are either like analyzed from an empirical perspective or from like a formal perspective, like we try to do in these papers to a large extent. And then there is a literature which I'm going to kind of talk more about because this is going to be one kind of upshot of our analysis about that treat memory maximization. So there actually is a literature that tries to maximize the memory capacity of some of these models by playing with the structure. And I will show you that this is kind of not such a good idea throughout this talk. I hope I will convince you of that. And then there is another definition of memory, which is called the Fisher memory. This is slightly different. It's related to memory capacity as I've defined it here in this talk, but we're not going to talk about that for this presentation. And also, it's not explicitly addressed in our paper because we really want to talk about this classical stochastic L2 measure of memory. So what's going to be the program then? I'm going to talk about two papers actually. So the first one is our 2024 paper on linear memory capacity. You will see this is interesting because it kind of sets the benchmark. So we started with the linear case because to some extent this is the easiest one that you can analyze in a it turns out not to be easy actually because at the end you have to do some algebra and the algebra at some point gets complicated as I will explain later in terms of like what you can formally write down, but it can be written down very explicitly, so this is the nice thing. So the thing that I'm going to show you is that the linear RNN or ESN case, if you want, that is of interest in our discussion is the memory is full. So this is a well-known result, or maybe not as well known as it should be, perhaps. There's not really much to do there in the sense that if you do a naive simulation, as I will show you in the next few slides, you don't really get this back. But this is because you have some algebraic issues that are built into this estimation problem. And so we actually show that what you can do is you can use this invariance of the memory capacity from the input. So from the construction of the input into the state, and in the linear case specifically, so there's going to be an input matrix that is going to load the z into the state equation, and the MC doesn't depend on that matrix. And so we can construct a numerically robust version of the memory estimator. But in fact, what it turns out that there really is no theoretical justifiable way to optimize memory of linear models because from the theory perspective, the memory is perfect. There's no problem there. And then the only problem is computing it and showing that this actually holds in practice, which I hope I'll show you is something that one can do relatively easily. With some algebra. And then the second paper, which I think will be the most, let's say, novel one, because it's the one that we've just put out in February, will be a natural extension. So what if you go to the nonlinear setting? Well, under quite realistic, I would say very realistic assumption, we're able to show that what matters for nonlinear model is really the variance of your input. So you cannot have this general, let's say, analysis, and as the variance grows or becomes small, you can touch any point along this interval bound between 1 and n. And so it is in fact sharp if you cannot say anything else about your sequence of inputs. So memory capacity by itself is going to turn out to be actually not very useful if you're interested in nonlinear models. Perfect. So if there aren't any questions about the setup, I would like to talk about the linear case first, and then we do the nonlinear case, and then I'm gonna give some final remarks. Perfect. So the setup for the linear case is gonna be very straightforward. So we're gonna talk about ESM models, as I mentioned in the introduction. These are given by equation 5 and 6. So the state equation is a linear state equation. The state is again xt, but you have this A matrix, square matrix loading xt minus 1. There is a C input matrix loading the input zt. So zt is usually smaller. I'm going to think in this case for simplicity that it is one-dimensional. So this is a one-dimensional stochastic input time series or process of some kind. I'm going to think about IID, but in the paper we give an extension of the results of the proof of invariance of the memory capacity. So what we use then later for the case of stationary, weakly stationary time series, if I remember correctly, or strongly stationary would certainly suffice. Then you have this intercept zeta. I'm going to remove zeta for simplicity of analysis. Because then it centers the state in terms of mean. Then YT is a linear projection of the state. So it's W transpose XT. Again, YT is going to be ZT minus tau, so it's going to be a one-dimensional lag of ZT. And in the cases where A and C and zeta are randomly drawn from a distribution, usually entry-wise chosen by the researcher, these are called linear ego-state networks. And we know that they have some nice approximation properties. This is what Ludmila and Juan Pablo worked a lot. So you can give, in the nonlinear case, for example, you can give nice generalization bounds, which might seem remarkable, but it's actually kind of a nice results in terms of representing filters in a certain appropriate way, and then you can see that one can basically sample the parameters of your RNN, and you still get a good approximation. What is important for us in the linear setting is that the memory capacity is easy to write down. This is in fact something that it's in a paper from Juan Pablo, Lucas, and Ludmila. Lucas Gonon, and you can write this down like closed form. So you minimize over the W taus, and then of course, you minimize the projection, and you can actually, I'll show you in a second, you can actually write down this 7 in closed form as a function of the variances and covariances of the X's and the Z's. But first, let me give you the core result about this class of models. So I'm going to call it the perfect memory result. And it says that, okay, we assume for simplicity that the zetas are equal to 0. We assume A to be diagonalizable with smaller than 1 spectral radius, so that, basically the states induce still a stationary process. It's not explosive. And that all the eigenvalues are distinct. So if any of the following three conditions that are on the slides hold, I think the easiest one to intuitively understand is A is full rank. Of course, and C is not the 0 vector and is not an eigenvector of A. This means that you cannot basically diagonalize the state by rotating in some basis. When you multiply A times C, A squared times C, and you go back in time if you unroll the state equation, then in such case, if you take a weakly stationary white noise process, the memory capacity is exactly equal to N. So the bound really is very sharp. It just tells you the memory capacity is full. And this is it in some sense. There's not nothing that we can say more under these conditions. But what the problem is how do you actually recover the memory capacity curves, for example? So not just say something about the memory capacity in theory, but actually see this in practice. So one thing that people do a lot, of course, and have done for a lot of time is Monte Carlo estimation. So I'm going to call this naive because it's, let's say, a classical approach. Very, very vanilla. You just simulate a process, you take the sample equivalent of whatever your statistics is, and then you use that to produce an estimate. So one can show, as I teased before, that the memory capacity at lag tau is just this function of the covariance between the zt minus tau xt, the variance of the states and the variance of the zt. So you can write this down closed form, and I'm gonna talk a little bit about this later, what this formula then implies algebraically. But you can run a Monte Carlo experiment. You just randomly generate your ACs and Z. Well, you assume Z is, I'm going to assume Z is zero, zeta is zero. You rescale the spectral radius of A so that you have a stable state equation. You do some warm up so that you know that you get close to the stationary distribution of the states. And then you just collect a length big T of states and of IID inputs, ZT, and you use the plugin estimators for all the covariances and variances. However, it turns out, and I'm not going to show you for the sake of time exactly how you write down the simulation bias that comes out of this, but it's available in closed form. We can talk about it later, perhaps, if you're interested. The problem is that there is a simulation bias, and this estimation method is imprecise. So I'm going to show you now plots of what comes out of this. And the first thing that is not encouraging is you seem to have not very good estimation. So here I'm showing you the memory capacity curves on the left, and then the total memory capacity on the right. It's normalized to be between 0 and 1 because I normalize it by the size of the system for clarity. So the memory curves are collected from the system is 100 dimensional, the state equation, and I go from 0 to 200, so 2 times the size of the system. The input mass comes from IID normal, and there's a uniform distribution connectivity matrix. So the A's are entry-wise standard normals with a spectral radius of 0.9. You can see that as we go from red to blue, so as T grows from 1,000 to 10, from I think 500 to 10,000, there's not much of a change. So there doesn't seem to be really good memory in this system. But we know that in theory, as I just showed you, there should be good memory, perfect memory, in fact. And an easy way to see this is to solve what I'm going to talk about in a couple of slides, which turns out to be a conditioning problem, numerical conditioning problem, because if you use an orthogonal connectivity matrix, this problem disappears. You can see that here we get different results in terms of the bias that I was talking to you about. So you can see that the red curve is kind of squashed more than the blue curves on the left, but the total memory capacity is essentially perfect at 1. So there's no undershooting. A different problem, though, is if you go from summing up 200 to 500 terms, so on the left, I haven't changed the z-axis, but now on the right, for the total memory capacity, I'm summing up 500 realizations of the MC tau, so tau from 0 to 500, you will see that there's significant undershooting even when t is 10,000. So when the ratio between n and t is 100, basically, which is it's a very strong ratio if you think about something like the central limit theorem. Indeed, you find that this does not align with the theory, right? Because we know that the memory capacity cannot be above n, and so these bars should all be below 1. So why is this happening? Well, with linear memory, it's an algebraic problem. If you write down the variances and covariances in closed form, you get the MC tau is equal to this expression 9, and let's say the meat of the sandwich that you have here in 9 is in the inverse of this GX matrix, which is an infinite sum of outer products of a to the power jc with itself. And so if you want to invert this object, you should think a little bit about what the properties are. The infinite term is not at all a problem. You can write this down in closed form by moving into the eigenbases of A. So this is perfectly available to you, no problem. And also the convergence when a spectral radius lesser than 1 is exponential. So you can write down a recursive loop for loop, and after 50 iterations, you're going to get there anyways to precision. But the eigenvalue structure is what creates significant issues when you want to invert the matrix. So I'm going to show you now the eigenvalues of the GX. And you can see indeed that if you have an orthonormal or a cyclic matrix, so these are the green and purple lines. I hope you can see them well enough. These decay exponentially fast, okay, but this is normal to some extent. If you think about powers of a matrix with a certain fixed spectral radius and the identity matrix as the easiest example of an orthonormal one. But if you then take a look at normal and sparse normal and uniforms, the decay is much faster. And so you touch numerical precision basically at 50 on the right hand side when n is equal 150. And then how do you invert a matrix like this? Well, you do, but not very well. This is the key issue.
Can I ask just one pure curiosity question? So what is sparse normal? It's like normal with some like Bernoulli masks, I guess, or something?
Yes, it's normal with a certain sparsity due to Bernoulli, for example, or yeah. So it's also entry-wise sparse. That's important. You can also do row-wise sparse. So some distribution are row-wise sparse or column sparse or this kind of thing. This is entry-wise sparse. Yeah, thanks for the question. Yes. So indeed, this is a very kind of big numerical problem, and hence we have to talk about the conditioning of the matrix. So I don't want to go too much into details about this because I also want to talk a little bit about the nonlinear case, but suffice it to say that the structure of the vectors that are involved in this outer product to construct the G. This is well known. It's the Krylov iterations, which is often used to recover, for example, leading eigenvectors and eigenvalues of matrices. And so the sequence C, A squared C, and so on to infinity, under the hypothesis that the rho A is more than 1, you get from Gelfand's formula, which is very well known, that the infinity norm of this AK diminishes, and so also the norm of all these vectors diminishes proportionally at some point. So one can use a truncation to an arbitrary order, basically, and derive an approximation that is, to find a numerical precision is perfect, essentially. And this is the outer product of this truncated Krylov iterate, Km, up to a to the n minus 1. The Krylov matrix that you get by doing the outer product, so the K transpose, the sum of the outer products, is well known to be very ill conditioned. So there is some theory by linear algebra people that this Krylov matrices have exponential lower bounds in them for their conditioning number. So you can also write down under some technical condition in proper theoretical bounds on the conditioning of these objects. What's important for us is that the MC you can actually write down as the rank of the Kn. This goes back to one of the conditions that was in the previous theorem that I didn't want to focus much on, but this is an important result because if you think about the QR decomposition, you have the Q factors, which are not so important, but then you have the R tridiagonal factors. And so the RJJ represents the norm of the orthogonal component of this iterate AJC with respect to the span of the previous column. So you can think of this as the orthogonal components of how much, if you want space, I'm adding, of course, normalized by the length of the vector. Every time I add this, I add another AJ plus 1C vector into my linear span, right? And ideally, we span all the way to N. But the question is, does this actually happen? For example, when RJJ diminishes super exponentially compared to the spectral radius of the matrix powers, like in the case I was showing you before. So in fact, we call this phenomenon, so this super exponential decay, and the associated loss in the spanning of space, Krylov subspace squeezing. And this is because basically you squeeze space, although in reality, this is not, in linear algebra, and this is not happening. It's only happening on your computer when you do this iteration. So what I want to focus on is not, for this slides, is just the very bottom, basically. So you can write down this perpendicular component of these iterate with respect to the previous linear span K calligraphic J of the Krylov iterates, and then you can write down the orthogonal component theta J, right? You can also write down as a projection matrix times this vector. The norm of theta J is thus the norm of this AJC times a projection matrix, because we're constantly doing linear projection operation basically when we want to recover these iterative perpendicular components. And so if you look at this one picture, which I think is really like the meat of the paper, you try to do basically, you try to recover the size of these orthogonal components by different methods. You can either use an Arnoldi iteration, which is one way of recovering basically these orthogonal components as residuals of the iterates you do for Krylov's algorithm to recover the leading eigenvector, or you do some orthonormalization too. So these are different algorithms that do essentially the same thing. And you will see that the size, so the length of the vectors we add in terms of adding more and more dimensionality or independent components in the state equation that we can load our inputs on and we can then reconstruct later, these decay so fast, so super exponentially. There's also in the paper an empirical, let's say very empirical conjecture that we make, which is that this decay can be very well defined as the cumulative product of the absolute eigenvalues of the A. So this is this eigen dotted line. We couldn't really, so I've also, I took some time also with some nice people, for example, in Nancy, talking about the mathematics of this, but there is no, as far as we could figure out, there is no easy way to get this cumulative product of absolute eigenvalues, but it's very it's a very good fit, and you can also write it down very nicely once you have this relationship in terms of random matrix theory. So this pops out kind of nicely to some extent in terms of the distribution of these eigenvalues if you think of a random matrix. But this decay kind of kills your memory properties unless you are in, as in the right-hand side, in the orthonormal case. And then you see the decay is very close to the standard decay you would get by simply taking powers of the row. So can we circumvent this algebraic issue? And this is the kind of, if you want the good part of the talk. The answer is yes. The trick is you can prove this input mask neutrality result with a little bit of algebra. So the MC tau turns out to be completely invariant to the choice of C for all the taus. And because of this, this result, which also holds under the stationarity, so you don't just need IID inputs, you can exploit this neutrality result to construct memory capacity curves for linear ESNs pretty easily. And the way to do this is very simple. You use the SVD. So in these slides, it's a little bit loaded with notation in terms of the SVD decomposition, but if you write down the SVD of the KM, you write down the KM transpose inverses and KM. This KM transpose KM, KM transpose minus 1 KM is the truncated form of your memory capacity. You write down the approximated, of course. You write down the SVD. You reduce all of the terms that cancels out, and you find V transport, which is the right singular factor in the KM. And this matrix is M by N, where, sorry, it's whatever length you have to. M by M. So M is the truncation you want. So let's say you choose 5 times M. This is going to be a 5 times N dimensional matrix. And then on the diagonals, you actually find the memory capacity tau. And this is what the equation tells you. So you can basically write down the SVD, which is better condition. You just write down these this product between matrices, and then you collect all of the diagonal terms. If you do that, you attain what we call the orthogonalite subspace method, because this kind of removes all of the dimensionality problem, the size problems. You just straight up doing the reconstruction of the directions that you have in the state equation. And if you average over multiple samplings, you get a better method, which is called the OSM plus. And as I will show you in these pictures, you can see that we reconstruct memory curves basically perfectly. So the blue one would be the naive when you make a simulation for on the left normal IID entry-wise normal A, and on the right when you add some sparsity, so 0.1 is the probability of having a zero. I think, or of having, sorry, it's the probability of having a non-zero value. Sorry. So the matrix is very large, so you're going to have actually this is not too bad. You're going to still have a lot of usable, let's say, memory. The capacity is full, so you recover this with both OSM, OSM plus, but you don't recover with standard OSM this monotonicity, which is well known to be a property of memory capacity. So the orange line is just an averaging over, let's say, I don't remember exactly, but this should be around 1,000 times, and you see it's perfectly monotonic, and it reconstructs the memory capacity well. So I've shown you basically everything that there is to know about the linear case, full memory. You cannot do naive things with the memory so much, but you can do less naive things by doing a little bit of linear algebra and then taking out the problematic part, let's say, and deriving basically a better condition estimator of your memory capacity. But the total memory capacity is full in that case. What happens in the nonlinear case? Well, this is the content of our most recent work, which we actually kind of derive along the linear part, but we wanted to be, I remember, we wanted to be more hopeful in the content of the paper, and then it turns out that we couldn't find a way to be more hopeful. So these are the results. These are the ugly part, if you want. So we just give a statement basically of the problem associated with memory capacity, as I will show you in a second. So to recap the setting, we are still in the equal-state network setting where the A and C are random. Again, there is no intercept, but there is a nonlinear term, a nonlinear activation function acting on the A xt minus 1 plus CZT. I'm going to choose a very specific, but not at all very restrictive type of sigmoid activation function. So this is a piecewise linearized activation function. So it's at least C1. It's monotonic increasing, of course. The important thing is that it's exactly -1 and 1 if you are, if you're pushing yourself to the very edges of the real line after some d, and then it's linear, exactly linear between minus delta and delta for a small delta. It's a very good description in terms of what you would get numerically if you took something like tan h. Because to precision, if you go very, very small, there is no difference between this type of approximation for delta small enough and d big enough with tan h. However, you have to connect, of course, these linear segments and constant segments correctly, but it's in principle doable. So if you have such an activation function, I'm going to show you two results, two theorems, if you want, that say that if you take our scale Rademacher input process, this is just for simplicity, so just something that is -1 and 1 with a certain variance, sigma, then the memory capacity, as you see it defined here, reminding you the previous definition I had, is going to be either full, so perfect, or it's going to be the worst case possible. It's going to be 1. And everything is going to hinge on the sigma. So why does the input variance matter? So to give you the intuition, the value of sigma, of course, scales the input. And so we can construct two proofs. And this is what is going to be the content of the rest of the talk. If we choose a sufficiently large sigma, such that the nonlinear ESN states only take extreme values, then this large sigma is going to imply a decay of memory. It's going to completely destroy the memory capacity of our model because we're just going to be ping-ponging between two different possible extremal states. And this is, of course, the worst possible case, right? Where intuitively, the realization of our state equation is it's entirely determined by the present realization of the input. So the past doesn't matter. The state is almost surely identical to some state that is achieved when we get +1 and some state that we achieve when we get -1 sigma. But if the state is sufficiently small instead, then because we have chosen an activation function that is piecewise linear, of course, what's going to happen is we're going to squeeze all of our states, as long as we do it, of course, strongly enough. We're going to squeeze all of our states into the linear regime. And then we know that when we are in the linear regime, it doesn't really matter. The memory capacity is full. This is just what we've been discussing in the previous part of the talk. So not only does as I was saying, the linear sigmoid provide a realistic kind of discussion, a realistic approximation of what you actually get in numerics, but it streamlines the proofs in the sense that it allows us to really see these two range acting in a clear way. So let me give you the first proof. This is going to be the lower bound. The lower bound is probably the most intuitive one in terms of construction. So let me walk you through it. You take the least entry of the C. So this is the least possible entry that you have in the C. We don't want it to be 0. This is an important assumption. We have to have the least entry of the input matrix to be non-zero. Then we take the floor L infinity of the Z, which is it has to be a little bit sophisticated. You have to go over all the possible, kind of events and all the possible T's, but the minimum realization of the ZT over all the possible entries of the Z. So in the simplest case, you can think of this as being, one-dimensional process, as I was showing you before. Then we take also the ceiling of the Z in L infinity. This is the essential supremum again over all the possible realization over all the possible times. And we're going to use this in the proof in terms of definition for the states and the inputs. So if you take the floor infinity, so the least possible case for the CZ plus AX in floor L infinity, this is certainly larger than, well, the smallest possible value you can get for CZ minus the largest possible value you can get for AX in CL and floor infinity. And so this is specifically larger than the C lower bar, sigma minus, we have to adapt with a constant square root n norm 2 of A. So whenever we choose sigma larger than square root n norm 2a plus d over c, and this is just in terms of construction of the sigmoid, remember, the linearized sigmoid, which means we stretch all the way to the part where it's completely flat. So all the possible entries of the x are either -1 or 1. We don't really care about which one it is, but they're all either -1 or 1. Then, in this case, the floor of the Z plus AX is greater than D, and so we're in this constant regime. We achieve two possible states. Phi of minus D, which is X minus the negative extremal states, and phi of plus D, which is the positive extremal states, depending on whether ZT, the current input to the state, is minus sigma or plus sigma. And so you can see that these extreme, as I was saying before, these extreme states or extremal states depend strictly on the sign of your current realization. So there is no memory in this system because it depends only on the contemporaneous input. Hence, MC is equal to 1, the worst case possible. The second bound is slightly more involved to design, but this is just because of the mathematics involved. So don't focus too much on the essential supremos and supremos that we have to construct. But the idea is if you seal the X, if you take the worst possible infinity case in terms of, sup norm of the states, you can write down the recursion. So the recursion in terms of time when you unroll the states. So this is the infinite series on the first line. This is strictly smaller than moving in the infinite to a 2 norm and then splitting out the a to the power of j with the czt's and adding some compatibility constants, of course, to move back into the infinity norm. We recovered the last line, which is this essential supremum of the square root n of the infinite sum of a norm to j times C upper bar, which is actually the maximal entry of the C times the sigma. And so you can, of course, write down the infinite series, convergent infinite series of the norm 2 of A, because we assume spectral radius lower than 1, and you get square root n over 1 over norm 2 of A, C upper bar sigma, right? So this is, in some sense, the really possible worst, highest possible state value that you can get. So this is kind of touching some kind of extremum. You need, of course, to use a bounded input stochastic sequence. If you have a Gaussian, this is not really gonna work. But if you use this for simplicity, this Rayleigh marker, then you find that sigma smaller than small delta 1 minus norm 2a over square root n c upper bar implies that this maximal L infinity entry of x is smaller than delta, and hence with our phi, we get a linear state because we are in the linear range of the activation function. But then the memory capacity is full. We have constructed a case where you reduce to a linear setting. So just to show you that this indeed works also if you do it in practice or in simulations, what you find is, okay, it's a nonlinear setting. So if you're not in the exact linear setup that you can use the OSM and OSM plus algorithms that I was showing you before, you cannot write down this in closed form. You really need to do simulation. So what I want to say is that if you compare A and B and C plots, the only A where we use our orthonormal matrix, you're going to get this nice linear setting. So when the sigma is very small and you are in this actual linear setting with a tan h, so numerical tan h, we're using pure numerical approximation here to go into this linear regime and constant regime. You're going to find perfect memory in the blue case with small variance, but then it's going to decay all the way to the red bar where you get 1, the worst case. If you go to sparse normal or simply normal, the conditioning is going to play a significant role, and there's no really easy way to interpolate between the linear case OSM method into a nonlinear OSM method, at least not that we could think about. So you're left with these simulations that are kind of not very nice when you are close to the linear regime, but indeed do decay all the way to the worst case scenario of MC equal 1 when sigma is large. Okay, so since I have a couple of minutes left, let me just give you the final remarks. And I'm just going to say there are 2 punchlines. For the linear case, the memory capacity, as I hope I've shown you, it's in some sense trivial. If you're really interested in the memory curves, then you can compute them with the algorithm I showed you. One comment you might have, do we actually recover the perfect memory curves? Is this consistent, for example? This we haven't studied yet, but indeed you at least solve the numerical conditioning issues that are built into the problem. So we definitely address at least what I think is one of the core problems. But if you're not interested in the memory curve itself, then there's nothing you can do. And there's certainly no design that you can come up with in this setup that maximizes memory in any reasonable sense of the concept, if your concept of memory is memory capacity, as I've shown you. For task specifics, nonlinear RNNs in Kalman setups, so wherein you assume nothing, let's say, or let's say you have a very broad idea of what type of inputs or stochastic inputs you want to feed into your ESN or nonlinear RNN, there's not much that you can say about memory capacity. If you know something about the variance, then maybe you might be able to say, okay, this is a good, we are doing a good normalization, which we know in practice people do a lot. They have to play a lot with normalizations and rescaling to make neural networks work. But this shows you exactly why this is so important. If you care about recall of your state equation of past inputs, then the variance really does play a huge role. And the last point is maybe an unfair question, but I find it really interesting to ask. I think it's a good question to ask. Of course, when we ask ourselves, I couldn't really answer. So maybe some of you might find a good answer for is: can we define let's say, principle, but a more useful metric for nonlinear models in terms of this idea of memory. Thank you very much.
Oh, thank you very much for the talk. Let me find the clapping emoji. Wow. Yeah, it's really actually very, very interesting talk.
Thanks.
I only have like maybe like one small question because I'll read the paper. But before, let me ask, does anyone in the audience have any questions? Well, everyone's always shy on Friday. I'm not sure. Yeah,
That makes
actually, I
sense.
just does it?
No, I don't know. Maybe.
And actually, just mostly just a thought, or like maybe just like a question. So for the so in your nonlinear models, you like you make your transformations and then you like activate with these like pretty cool activation functions actually. Um, I'm just curious if you then afterwards, after activating, add some small Gaussian noise or something like this, would that fix like this memory problem? Because like yeah, by whitening, I'm wondering if like the involved matrices will become like well conditioned, you know?
Oh, you mean if there is? So actually,
Like at
I know
every
of a
step, you just sample like a independent Gaussian after activating.
So this, so intuitively, I know that like adding like noise in equation is usually something close, right, to basically doing ridge regularization if you
Yeah,
want.
something like that. Yeah, yeah, true. I guess so. Yeah, yeah.
So I've done some work on ridge, and my usual perspective is if you really want to touch the spectrum of your
Exactly.
uh, estimate, you can either you only can do it in two cases. One, you don't care about the spectrum of your thing because ridge is kind of a nuclear option usually. Or two, you have a very good idea of where
Yeah.
you want to how you want to touch it up.
Mhm.
So in the first case, I can say. You can do it, definitely. You could do this. So, in fact, there's a recent paper, but I forgot the authors now. But we were in a workshop where it was
Cool.
discussed this, where they study the memory in the case where you have noise in the state. So exogenous noise. You cannot
Yeah.
control it, but it's built
Yeah.
in. And so they study the linear case also with this noise. And indeed, it smooths out things, but it's also drowning out the memory a little
Yeah.
bit. So it's a give or take
I see. I see.
depending on how you care. And in the second case, well, I know, for example, if you think about financial econometrics there and you want to estimate some covariance matrices in high dimension, so um, people have worked on this a lot, and turns out that there are specific ways, very clever ways of touching up the eigenvalues
Okay.
in a specific nonlinear way where this gives you some improvement.
Cool.
Otherwise, you have to assume that the noise is very small or as
Yeah.
the sample size grows and all these kinds. So there's a rate that you have a rate game that you have to play. So it's a very good question. Uh, Off the top of my head, I would say maybe that's something if you want to do maybe nonlinear memory. Maybe there
Mhm.
it might be worthwhile
Yeah.
with some rule of thumb on how much you add. But in the linear case, I don't see it so much.
Yeah.
Yeah.
No, I wasn't for not the non-linear. The linear, it's like it's already looking
Yeah,
pretty
yeah,
good.
yeah, yeah. So maybe that's something. Maybe it would be good in the nonlinear case,
Sure.
yes. But
Yeah.
the tuning of it would be tricky, I would say. So one would have to have an idea of how this decay happens,
Sure.
what the structure is, and I can tell you if you do simulations, it's better than the linear case, but it's not that better,
Hmm. Okay. Okay.
depending on how the variance is, right? Um, because the structure of the problem is quite complicated. So also this decay in the linear case is not easy to write down in closed form. So in the nonlinear case, I don't have much of a clue. Yeah.
Maybe I can ask like a one more pure curiosity question. Uh, Actually, what would be your answer to your last question? Like, I mean, not answer, but do you have any idea of how you would define memory in the nonlinear case?
So
If I can ask, if you
so
don't want to
I,
talk about it online, you cannot.
no, 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 it's fine. I mean, I think it's fair. I mean, I have so initially, okay, I can tell you what I tried. So, okay, we define a measure where we normalize by the variance. So you introduce the concept of a second moment, and then you normalize by the second moment of the
Mhm.
process. But the problem is that you cannot really play this game because you also have to play with the scaling of the input matrix, which is another thing that you can play with. So in practice, when you implement these, RNNs, the scaling, the normalizations, these are all important things that practitioners play a lot with. Not only the transformations of the data, but also the normalizations of the in the randomly sampled initial values for the neural network, for example, so that it's not in a bad part of the loss landscape. And there I couldn't, so you can write it down, but then it's still dependent on some, implicit idea that you normalize, and then there's an hyperparameter, but then how do you rescale different entries? So there you have all these concepts. So it wasn't very fruitful. I would say maybe something based on entropy or this kind of more sophisticated, a more sophisticated approach that involves really like distributional properties, not just second moments. Not this, so this L2 measure is in some sense very crude, right? And we know that it is because, I mean, for the last, 20 years, I would say people have worked with, I mean, even if you work with Kullback-Leibler or Wasserstein or optimal transport and these kind of things, you know how much there is to gain there in terms of robustness and effectiveness when you move to studying the whole distribution, not just some finite number of moments. So I would say something like that. It seems to me like that's somewhat natural. How to exactly do it, I'm not an expert in this kind of thing. So yeah, I would have to think about it. I think a couple of years more, maybe.
Not sure. I mean, that's the whole point of research, I guess.
But
No,
it's
but
a great
honestly,
question. Yeah, yeah.
yeah, honestly, it's a pretty great talk. Let me just stop the